Hi, welcome to Orozco's Lectures. I am Jose Orozco, and these are my lectures. This lecture is a Calculus 2 lecture. I hope you enjoy it. This is 7.1 Advanced. So by that I mean we just mean the advanced exercises. And by that we mean, well, we've been talking about, we already spoke about a whole bunch of integration techniques, right? So let's find some areas that require us to use some of those integration techniques. So let's say, for example, I have the function f of x is equal to 3x plus 2 over x squared plus 9, and I want to find the area under that curve from 0 to 5. All right, so here we go. In this region, well, we're going to say, well, the area is the integral from 0 to 5 of 3x plus 2 over x squared plus 9 dx. All right. Now, the very first thing I'm going to do here is, well, since we already spoke about integration techniques, I'm going to split this up into two. So I've got these two different integrals. I'm going to write this as 3 times x over x squared plus 9 dx plus 2 times the integral from 0 to 5 of 1 over x squared plus 9 dx. All right, and the reason I'm doing that is because we're going to have two different techniques to these two integrals. So this first one, I'll do in blue. So we have 3 times the integral from 0 to 5 of x over x squared plus 9 dx. All right. So here, it's a u substitution. If I let u be equal to x squared plus 9, then du is 2x dx. So that dx over 2, so that du over 2 is our x dx. And I want that because here I have x dx. So what that gives me now is, that gives me the integral, well, 3 times the integral from 0 to 5 of this x dx. That was our du over 2. So I'm going to put it over 2, and I'm going to write it as 1 du. This x squared plus 9, that's our u. So this integral becomes 3 halves. Oh, hold on, not from 0 to 5. Let's change that. Let's see what the new bounds are supposed to be. When x equals 0, u equals 9. When x equals 5, u is 34. Right? 5 squared, 25 plus 9, 34. 0 squared plus 9 is 9. So we're going from 9 to 34. There we go. And we have 3 halves, ln of the absolute value of u, evaluated from 9 to 34. So we get 3 halves ln of 34 minus 3 halves ln of 9, using rules of ln and factoring out the 3 halves, and then with 3 halves ln of 34 ninths. All right, so that's the first part. The second part, let's do that one in yellow. So that integral we'll do in yellow. So we have 2 times the integral from 0 to 5 of 1 over x squared plus 9 dx. This is arctan, right? This becomes 1/3 arctan of x over 3. X over 3. And this is evaluated from 0 to 5. So what I get here really is 2/3 arctan of 5 minus 2/3 arctan of 0. Arctan of 0 is just 0. So what we really have here is just 2/3 arctan of 5, whatever that is. So our overall answer, well, let's see. This integral, the sum of these two integrals, we're going to add up the blue and then add up the yellow. Or I should be saying add up the blue with the yellow. So we've got 3 halves ln of 34 ninths minus 2/3 arctan of 5. All right, now this is approximately equal to 2.68. That's a calculator answer, but this part right here is what I would be expecting because that's the exact form. All right. In terms of the graph that we just found, well, let's see the area, the region. It looks something like this, right? Where over here somewhere is 5. So that's the region, the area of the region that we found. Units squared. Okay. Next one. So that was A. B. Let's say that I had the following. Y squared is equal to x squared times 1 minus x squared. And we're going to do this from 0 to 1. All right. So let's see what we get here. Now, the first thing that I want to note here is the following. If I were to plug in negative y as well as negative x at the same exact time, well, negative y squared is just y squared. Negative x squared is just x squared. And negative x squared is just x squared. And look at that. That's the original equation. What this tells me graphically is that this equation is symmetric about the origin. All right. So what that means is it's symmetric about both axes. So let's see what that. Well, in here I should be saying symmetric about both axes, not just the origin. About both axes, both the x and y axis. About both the x and y axis. All right. So graphically speaking, this is what the function looks like. All right, and I'll draw it here. So it looks like this. That's not function. This equation. It's not a function. Kind of like similar to like an infinity symbol. All right, where this value right here is 1, this value right here is -1. All right, the intercepts. And what we're looking for here is this region, this entire piece over here. Because I said from 0 to 1, right? So I'm looking for this piece right here. So what we're going to do is, well, we're going to say, well, this equation, that y squared equals all that stuff. That's the same thing as saying y is equal to plus or minus the square root of x squared times 1 minus x squared, which is the same thing as saying plus or minus, well, the square root of x squared is just x, so x times radical 1 minus x squared. And in here, well, we have a positive and a negative version. This top piece above the x-axis is a positive version. This bottom piece below the x-axis is the negative version. So to figure out this entire area, well, this piece, this area 1 is the same thing as area 2. So I could just figure out area 1 and multiply it by 2, right? So that's what we're going to do. So we're going to say the area is going to be twice the integral from 0 to 1 of just the top piece, which was the square root of, x times the square root of 1 minus x squared dx. And well, in here there's multiple ways to solving this one, right? The obvious one that comes to mind is u substitution. We could also do this with trig substitution if we wanted to, but we're going to do this with u substitution. So let u be equal to 1 minus x squared, so that du is negative 2x dx. So we know that du over negative 2 is just x dx, right? X dx. So that's going to replace that du over negative 2. Now, we need to change our bounds. When x equals 0, u equals 1. When x equals 1, u equals 0. All right, so now, what do we get? And again, all I'm doing there was plugging this 0 and 1 into here to figure out the values of u. So I get now twice the integral from originally 0 to 1, Now from 1 to 0 of x dx, well, that x dx was du over negative 2, so du negative 2. And this 1 minus x squared, that was just u. This radical sign, I'll do it as a power to the 1/2. And at that point, this 2 over negative 2 becomes negative 1. Well, actually, let's this negative value and these bounds. I can flip the bounds and get rid of the negative. 2 over 2 is just 1, so we don't write it. And we still have u to the 1/2 du. And in here, the integral of u to the 1/2 is u to the 3/2 divided by the new exponent, which is the same thing as saying multiplied by the reciprocal. And we're doing this from 0 to 1. And when we do that, well, we end up with 2/3 times 1 to the 3/2 minus 2/3 times 0 to the 3/2, which is just 2/3, right? So that 2/3 represents that entire area right there in blue, because again, we multiplied that area sub 1 times 2 to get that entire area. And if we wanted both of these, right, like if I wanted this piece too, I would have just needed to multiply the entire thing by 4. That's this region right here by 4, right? So instead of 2, there would have been a 4 there. All right. Next example. That was B. C. Let's say that I have y equals x sine x, and we're going to do this from 0 to pi, all right? And I'll give you a general visual as to what this is, all right? Here's a vertical line, and it kind of looks something like this. Well, and it kind of just repeats forever and ever, all right? And where this value right here is 0 and this is pi, so we're figuring out that region right there. All right, so we say the area is going to be the integral from 0 to pi of this thing, x sine x dx, all right? And in here, well, how do we do something like this? Well, this would be integration by parts, all right? This is going to be integration by parts, but I'm going to do the tabular version of it. So I'm going to start with u being x, take derivatives. dv being sine of x, take integrals. So I get negative cosine x, and then get negative sine x. Next thing, ignore the last thing under the u's and the first thing under the dv's. Do a plus minus plus on the outside, alternating. Multiply diagonally. So we end up with here x times negative cosine x, or negative x cosine x, minus 1 times negative sine x, so plus sine x, evaluated from 0 to pi, right? And what do we get? Well, let's plug in pi, so we get negative of pi times cosine of pi plus sine of pi minus the negative of 0 times cosine of 0 plus sine of 0. Okay, so what do we get here? Sine of pi is 0. 0 times cosine of 0, well, cosine of 0 is 1, but 1 times 0 is 0. Sine of 0, 0. So I get negative pi times cosine of pi. Cosine of pi is negative 1. So my answer there is just pi. So next one. So that was what? C? All right. D. All right, let's make this one a little bit more exciting. It's going to be a little bit more theoretical. All right, but let's find the area of an ellipse. All right. and here just get the generic area of any ellipse. All right. So let's see what we can do here. The formula for an ellipse centered at the origin will be x squared over a squared plus y squared over b squared is equal to 1. All right. In there, that's talking about, well, we're centered at the origin, so we have something like this, where this value is a, this value right here is negative a, this value here is b, and this value right here is negative b. All right. In here, notice that this distance, this width, going this way, is 2b. And then this distance going this way is 2a. All right. Now, I bring that up because, well, this there's already a formula for the area of an ellipse, right? And in fact, I'll tell you what the formula is right now. The area of an ellipse, given these dimensions, is just AB times pi. All right. So if this is whatever this diagonal distance is divided by 2, that's our A. This vertical distance divided by 2, that's our B. So that's the area. But why? The question here is why? Why would that be the area? All right. So let's figure something out here. Let's first solve for y here. All right. So move the x squared over. So I have y squared over b squared is 1 minus x squared over a squared. I'm going to come up with a common denominator on the right hand side. So I have here a squared minus x squared over a squared. Multiply both sides by b squared. So y squared is equal to b squared times a squared minus x squared over a squared. Take the square root of both sides. So y is plus or minus b over a, right? The square root of b squared. Well, perhaps we'll do this in 2 steps. The square root of b squared over a squared times a squared minus x squared, right? And in here, the square root of b squared over a squared, well, that just becomes b over a. So I have b over a times radical a squared minus x squared. Now, why did I want that? The reason I wanted that is because, well, in here, this top portion represents the positive version, and this bottom portion represents the negative version of that y. All right. So what we can do here is, well, similar to what we just did in that one example, not this one. In this example, where we're going to take the top and multiply it by 2 to figure out that entire region. So that's what we're going to do here as well. All right. And we're just going to take the positive version and multiply it by 2. So here we're going to have that the area is going to be the integral from, well, from what to what? From a to a, excuse me, from negative a to a. The integral from negative a to a. And we said we're going to be doing twice the integral of b over a times the square root of a squared minus x squared dx. This b over a, let's take it to the outside. So we have 2b over a, integral from negative a to a of radical a squared minus x squared dx. All right, so now in that integral, let's do that integral by itself. We'll worry about this 2b over a later. So let's look at that integral. So we have the integral, and I worry about the bounds later too. So we have the square root of a squared minus x squared dx. In here, we're going to do trig substitution. We're going to say let x equal a sine theta. Then dx would be, well, the derivative, a cosine theta d theta. So this integral now, it becomes, well, the integral of the square root of a squared minus a sine theta squared, right? That was our x, and the dx is going to be a cosine theta d theta. All right, so let's do a little bit of side work here. This, what does that become? Well, the square root of a squared minus squaring these, I get a squared sine squared. They both have an a squared, so we can factor that out. So I have a squared times 1 minus sine squared. 1 minus sine squared is just cosine squared, so I end up with a squared cosine squared, and square rooting that, I end up with a cosine theta. So what I end up with now is that entire thing was a cosine theta, so I have a cosine theta times a cosine theta d theta. So what I really have there is just the integral of a squared cosine squared. I'll put the a squared on the outside. A squared cosine squared theta d theta. Which, well, how do we deal with that? What we're going to do here is we're going to do a power reduction formula. All right? We're going to do here a power reduction formula for cosine squared. And the power reduction formula for cosine squared would be 1 plus cosine of 2 theta over 2 d theta. All right, I can pull that over 2 out, right? And what I have here really is just a squared over 2 times the integral of 1 plus cosine of 2 theta d theta, giving me a squared over 2 times theta plus the integral of cosine is sine, so sine of 2 theta over 2. All right, that's technically a U substitution problem, but you put it over 2. Technically, we're going to say here plus c, right? Now, because here I was doing with the I was on an unbounded integral, right? Which is why I do the plus c, an indefinite integral. So what I get now is, well, let's see. I have here that x is equal to a sine theta. So what does that imply? Since x is equal to x sine theta, I get that x over a is sine theta, right? I just divided by a. And this implies some triangle. Let's see, here's theta. Sine from SOHCAHTOA, opposite over hypotenuse, making this side over here a squared, the square root of a squared minus x squared. All right, so the other thing that this implies is that theta is sine inverse of x over a. So let's see how that helps us here, right? Because I can't leave things in terms of theta. So I have a squared over 2 times theta was sine inverse of x over a plus, sine of 2 theta. Well, I can't do anything with that yet. So let's write it as 2 sine theta cosine theta. And we have that over 2 and plus c. Well, these twos cancel out. And I have a squared over 2 times sine inverse of x over a plus sine theta. Sine theta we know to be x over a times cosine theta. Cosine theta, well, it's adjacent over hypotenuse, so I get radical a squared minus x squared, right? That's our that's our adjacent over hypotenuse of a, and we have that all plus c. Distributing this a little bit, right? I'm going to distribute this a squared over 2, so I have a squared over 2 sine inverse of x over a plus this a squared, and these two a's are going to cancel each other out. So I really just have x over 2 times radical a squared minus x squared. And then plus c, right? At that point, well, what can we actually do there? That was just the blue integral, right? We're still missing this 2b over a, and we're still missing these bounds. So let's go ahead and apply that. So now what we can say is we had 2b over a times this integral, which was a squared over 2 sine inverse of x over a plus x over 2 radical a squared minus x squared. And now we're going to say this is supposed to be evaluated from negative a to a. So let's see what we get here. Distributing this 2b over a into each of these. Well, in this first part, the 2's cancel out, one of the a's cancels out, so I end up with ab, right? These 2 cancel out and these a's reduce. So AB times sine inverse of x over a plus 2b over a times this. Well, the 2's cancel out, and I end up with bx over a times the square root of a squared minus x squared. All right, and all of this evaluated from negative a to a. So now let's evaluate this. All right. Well, I need to plug in the top, then plug in the bottom. So I end up with, let's plug in the top. AB times sine inverse of a over a plus b times a over a times the square root of a squared minus a squared. Right, that's plugging in the top. Minus plug in the bottom, negative a. So I end up with ab times sine inverse of negative a over a plus b times negative a over a times the square root of a squared minus a squared. So that's plugging negative a in there. And in there, let me just rewrite that as the negative of a squared. All right. Now, let's see what we get here. Notice here that a squared minus a squared is 0. So here I just have the square root of 0. So this goes to 0 along with this, right? This entire thing goes to 0. Similarly over here, negative a quantity squared is positive a squared. So this goes to 0 along with this. So what do I get now? I get ab times sine inverse of a over a, which is just 1, minus ab times sine inverse of negative a over a, which is just negative 1. And at that point, we say, well, sine inverse of 1 is pi over 2. So I have ab times pi over 2, right? Because that's the angle that makes sine be 1, right? Sine of pi over 2 would be 1. Similarly, sine inverse of negative 1, well, that would give me negative pi over 2, all right? Because that is the angle in which sine inverse gives us, in which sine gives us negative 1, negative pi over 2. So in here, what we really have now is, well, they both have an AB. I'll factor out the AB. And what we have is pi over 2 minus a negative pi over 2, which is plus. So pi halves plus pi halves, that's just pi. And there we go. That is the formula for the area of an ellipse. All right. We could do something similar like this if we wanted to figure out the area of a circle, for example. All right. But I will leave that up to you to try to figure out by yourself. All right. So that concludes the advanced examples of area. Wasn't that fun? If you think I made a mistake somewhere, you're probably right. Tell me all about it in the comments. If you feel you learned something from me in this video, hit the like button, hit the subscribe button, but more importantly, share it. Share this video with your classmates. And remember, you don't have to like math in order to be good at it. But you do have to be good at it. I am Jose Orozco. Goodbye.